All right, today on topic 6.7, we need to start off with another piece of information of the fundamental theorem of calculus. This is another component of the fundamental theorem of calculus. It says that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where that capital F is an antiderivative. So we're going to be learning how to find the actual antiderivative in topic 6.8. But today, we're just working through this idea of if I know the antiderivative, then all I have to do is plug in the top limit and subtract it from plugging in the bottom limit. All right? Once I know the antiderivative. And the idea is that we're going backwards, all right? So just real quick before we tackle this problem, if I have a function f of x, its derivative is f prime of x, right? Well, if I integrate f prime of x, I will get f of x. It's simply going backwards. That's the idea of an antiderivative, and we will learn how to do that in topic 6.8. All right? So it's just this idea, if you can kind of view this circle, this was all part of Sir Isaac Newton developing the fundamental theorem of calculus, is this idea, this relationship between derivatives and integrals. All right? So, if they ask us for, let's look at this problem. The graph of y equals f of x is shown at the right. What is the integral from 3 to 1 of f prime of x dx? Well, from what I just told you, this is going to be the antiderivative of f prime of x is going to be f of x. So all I need to find, based on this fundamental theorem of calculus I told you up here, is I just need to do f of 3 and subtract f of 1. All right, and we can get that from our graph here. All right, f of 3 is 6, f of 1 is 2, so my answer is 4. So once again, this relationship down here in the corner is very important. Understanding that when I find an integral of f prime of x, it takes me back to the original function. All right? All right, let's take a look at this second problem. This is a tabular problem. The table above gives values of a function f and its derivatives at selected values of x. If f prime is continuous on the interval -4 to -1, what is the value of the integral from -4 to -1 of f prime of x dx? Well, from what we just learned, the integral of the derivative of a function leads us to the antiderivative, that capital F that we talked about. All right? So I want to show you a new kind of notation. What we can do is we can put that original f of x there. We can put a little bracket around it like this, and we can put our limits of integration like that. And what that tells us is it tells us what to do. it tells us that we are going to find f of negative 1, and we're going to subtract f of negative 4. So you do need to be familiar with that notation. And, how convenient, we have those values in the table. F of negative 1, all right, is right here, negative 1.5. And we subtract f of negative 4, which is 0.75. And our answer is negative 2.25. Keep moving. If g of x is an antiderivative for f of x. All right, that's an important statement. And g of 2 equals negative 7. And g of 2 equals negative 7, then they want to know what's g of 4. So what we're really looking at, first off, let's make this statement. G prime of x is going to equal f of x. All right, if g is the antiderivative, well, if I take the derivative of g, I'm going to get f of x. All right, so if I find the integral from 2 to 4 of f of x dx, it's going to be g of x evaluated from 4 to 2. All right? And so this is going to be g of 4 minus g of 2. All right? And that equals my integral from 2 to 4. And let's press pause for a moment, because sometimes you get into problems and you think, am I going to have enough information to do this? If we look at our answers, my answers are not a clear number. They are expressions. So keep that in mind. They are expressions, all right? So if you look at what we've been given g of 2, which is negative 7. So now I can put that in. G of 4 minus a negative 7 makes this plus 7 equals that integral from 2 to 4. All right, so that means that if we do a little bit of algebra, that g of 4 has got to be negative 7 plus the integral from 2 to 4. And we can see that's one of the possibilities here. Right here. All right, the derivative of a function h is this expression here. What is the integral from 2 to 3 of this thing right here? All right. Well, if we think of, if I integrate the derivative of something, I get the original function. Remember that. And so if I was integrating this from 2 to 3, I would be evaluating the original function from 2 to 3. All right? So all we have to do is, it's letter C. All right, because all we did was we worked backwards. It's going to be, from this, we know it's h of 3 minus h of 2. All right. We're just working the fundamental theorem of calculus here. All right. This problem is one of those classic ones that looks like it just has so many things going on, but it's really not that bad. All right. Temperature of water in a tub is modeled by a strictly increasing twice differentiable function, W, where W is measured in degrees Fahrenheit and T is measured in minutes. So we're talking about the temperature. At time T equals 0, the temperature of the water is 55 degrees. The water is heated for 30 minutes, beginning at time T equals 0. Values of W of T at selected times T for the first 20 minutes are given in the table above. So our question is, use the data in the table to evaluate the integral from 0 to 20 of W prime of T dt. Well, this is going to be just the original function evaluated from 0 to 20. That's all that is. So that's going to be W of 20 minus W of 0. All right, and we can get that all from the table. This is going to be 71 minus 55, which is 16 degrees. All right. So we started with what was W prime of T? W prime of T was how fast the temperature was changing. Okay, this was describing the rate of change. Okay, when we integrate the rate, if I integrate the rate of change, remember that leads me back to some type of position or amount. All right, and so that's how we came up with an amount here. All right, which is what we were dealing with. One more problem. We're working from the same table, by the way. This is part D. For 20 to 25, the function W that models the temperature has first derivative given by W prime of T equals that thing. All right. Based on the model, what is the temperature of the water at time T equals 25? Okay. Well, what we can do is we can say that the integral from 0 to 25 of W prime of T is equal to the integral, sorry, not the integral, the temperature minus, I said minus, I meant to say plus, our change, what is our amount from 20 to 25? All right, because we were told what was happening at time 20. Okay, we were told what was happening at time 20. So if I add this amount from 20 to 25, then we'll be good. And this is use your Math 9 on the graphing calculator, and that is 2.043. Add that to my 71, and we get 73.043. And we will stop there for today.